Imagine a place where the very fabric of reality is stretched and tested with an intensity found nowhere else on Earth. Far beneath the quiet farms and villages that straddle the border between France and Switzerland, a vast underground ring nearly 27 kilometres in circumference hums with power. This is CERN, the European Organization for Nuclear Research, and the heart of its most ambitious creation, the Large Hadron Collider. For decades, this machine has smashed particles together at energies that briefly recreate the first moments after the Big Bang, confirming theories that once seemed pure fantasy. Yet in December of 2025, something unexpected appeared in the data. A signal so strange, so quietly defiant of every established prediction, that even the most experienced physicists found themselves staring at their screens in silence. The numbers did not match the rulebook. They were not dramatically wrong, not the kind of discrepancy that sets off alarms and flashes red lights. They were simply, stubbornly wrong in a way that should not have been possible. A rare type of particle decay, studied with exquisite care over years of collisions, was refusing to behave the way the standard model insisted it must. The deviation was small, almost polite, yet it refused to disappear no matter how many times the data was cleaned, reanalyzed, and cross-checked. In the control rooms and analysis meetings, a quiet tension settled. Careers that had been built on the near perfection of the existing theory now faced the possibility that the map of reality itself contained a hidden flaw. If you have ever looked up at the night sky and felt the pull of questions larger than any single answer, this is the story for you. Before we go further, take a moment to like this video and subscribe to CosmoDepth if you have not already. We explore the frontiers where science meets the deepest mysteries of existence, and the road ahead is long. What the detectors recorded that winter was not a new particle arriving with fanfare. It was a subtle preference, a statistical tilt in how certain heavy particles, known as B mesons, chose to fall apart. According to the most successful theory in the history of science, two families of particles called leptons should have been treated almost identically in these decays. Electrons and their heavier cousins, the muons, were expected to appear with nearly equal frequency once mass differences were accounted for. The data said otherwise. One path was favored over the other, consistently across independent analyses and larger samples. The effect was not yet strong enough to claim a definitive discovery, but it was strong enough to keep senior scientists awake at night. The machine that produced this quiet rebellion is itself a marvel that borders on the impossible. Protons, the dense cores of ordinary hydrogen atoms, are accelerated in stages until they race around the buried ring at 99.9999999% of the speed of light. Two beams travel in opposite directions and are steered into head-on collisions 40 million times every second. At the moment of impact, the energy density briefly reaches temperatures more than 100,000 times hotter than the center of the sun. For a vanishing fraction of a second, a tiny region of space becomes an echo of the newborn universe. Detectors the size of multi-story buildings surround these collision points, recording the spray of new particles that flash into existence and vanish almost instantly. Most of the time, the wreckage behaves exactly as predicted. In December 2025, a small corner of that wreckage did not. The people who first noticed the anomaly did not celebrate. They checked, they rechecked. They argued over systematic uncertainties, background estimates, and possible software artifacts. Months of meticulous work followed. independent teams examined the same data with different methods. The discrepancy remained. What began as a statistical curiosity hardened into a persistent signal that the theoretical community could no longer ignore. Somewhere in the delicate quantum processes governing these rare decays, something unknown appeared to be reaching in and tilting the odds. This is not the first time the Large Hadron Collider has surprised its creators. It delivered the Higgs boson in 2012, the long-sought particle that explains how other particles acquire mass. That discovery completed the Standard Model and felt like the closing of a chapter. Yet the model has always carried known gaps. It cannot describe gravity at the quantum scale. It offers no particle that could account for the invisible dark matter holding galaxies together. It cannot explain why the early universe produced a slight excess of matter over antimatter, the imbalance that allowed stars, planets, and life to form at all. The anomalies of recent years, including the one recorded in 2025, may be the first faint fingerprints of the physics that fills those gaps. The story that follows is the story of that signal and of everything it connects to. It is the story of a machine that can recreate the dawn of time, of detectors that act as the most sensitive cameras ever built, and of a growing collection of small, stubborn deviations that refuse to be explained away. It is also the story of the people who spend years underground and in analysis rooms, chasing numbers that might rewrite the foundations of reality. We begin deep underground, with the machine itself, and with the quiet moment when the data first whispered that the rulebook might no longer be complete. The deeper we go, the stranger the questions become. And the answers, if they come, may change more than physics. They may change how we understand the fact that anything exists at all. The journey into the heart of CERN begins long before any particle ever reaches the main ring. It starts with something almost ordinary, a bottle of hydrogen gas. From that simple beginning, the protons are stripped of their electrons and fed into a chain of accelerators that gradually raise their energy in carefully timed stages. First, a linear accelerator gives them their initial push. Then, they enter a series of circular machines, each larger and more powerful than the last, until finally they are injected into the vast 27-kilometre loop known as the Large Hadron Collider. By the time they complete that final transfer, they are travelling so close to the speed of light that a single proton can circle the entire ring more than 11,000 times every second. Picture the tunnel itself. It is a concrete corridor wide enough for a small vehicle, lined with thousands of superconducting magnets, each one a precision instrument weighing tens of tons. These magnets are cooled by liquid helium to temperatures colder than the dark space between the stars, just 1.9 degrees above absolute zero. At that extreme, the cables lose all electrical resistance and can carry the enormous currents needed to bend and focus the particle beams without melting. The vacuum inside the beam pipes is equally extreme, emptier than the surface of the moon, so that the racing protons encounter almost nothing that could deflect them from their paths. Maintaining these conditions across nearly 27 kilometers of underground tunnel is an engineering achievement that borders on the miraculous. When the two beams finally cross at 4 designated points around the ring, the collisions are not random acts of destruction. They are deliberate recreations of the conditions that existed fractions of a second after the Big Bang. For an unimaginably brief instant, the energy density at the collision point climbs to more than 100,000 times the temperature at the center of the Sun. In that fleeting fireball quarks and gluons, the fundamental constituents of ordinary matter, are briefly set free from their usual bonds. New particles flash into existence and decay almost immediately, leaving trails of energy and charge that the surrounding detectors must catch and interpret. 40 million such collisions occur every second. The raw data stream is so vast that only a tiny fraction can be saved. Sophisticated trigger systems decide in real time which events are interesting enough to keep. The people who operate this machine live with constant vigilance. A microscopic dust particle, a tiny shift in the Earth's magnetic field, or a momentary fluctuation in the power grid can disrupt the delicate balance of the beams. In the main control room, teams from dozens of countries watch banks of screens around the clock, adjusting parameters, diagnosing problems, and keeping the collider running for weeks or months at a stretch. There is little drama in the day-to-day work, only the quiet concentration of experts who understand that every successful fill of the ring represents years of preparation and the collective effort of thousands. Yet, it is precisely this extraordinary precision that makes any unexpected signal so powerful. When the machine is working at its best, the standard model's predictions have been confirmed again and again with almost irritating accuracy. That long record of success is what makes the rare deviations matter. If a particle decay begins to behave in a way the theory cannot explain, the discrepancy cannot easily be dismissed as experimental error. The same instruments that have verified the rulebook so thoroughly are now recording something the rulebook did not anticipate. Standing in the tunnel when the magnets are cold and the beams are circulating is an experience few outsiders ever share. The air is still. The only sounds are the soft hum of cryogenic systems and the occasional distant echo of footsteps. Overhead, hundreds of meters of rock and soil separate the machine from the ordinary world of farms and villages. Down here, the universe is being asked questions it has never been asked before, at energies that briefly erase the distinction between matter and pure energy. The detectors that surround the collision points are the true eyes of the experiment. Each one is a multi-layered instrument the size of a building, packed with sensors that track, identify, and measure the particles streaming outward from every crash. Some are designed to catch everything. Others are specialized, tuned to particular types of particles or particular kinds of rare processes. Together, they form a global network of observation, feeding data to computing centers on every continent, so that thousands of scientists can examine the same events from different angles. It was one of these specialized detectors that first recorded the quiet anomaly of December 2025. While the great general-purpose instruments searched for dramatic new particles, this more focused experiment was patiently watching the way certain heavy particles fell apart. Year after year, it accumulated statistics, building a mountain of data so large that even the rarest decays could be studied with confidence. When the numbers finally refused to match the predictions, the discrepancy could not be ignored. The machine itself continues its work. The beams keep circulating. The collisions keep happening. And somewhere in the vast streams of data, the same stubborn signal continues to appear. A small but persistent reminder that the universe may still hold secrets the current rulebook has not yet written down. The deeper we look into the details of that signal, the more clearly we see that the story is only beginning. The true power of the Large Hadron Collider is not only the energy of its collisions, but the extraordinary instruments that surround them. 4 great detectors stand at the points where the proton beams cross, each one a scientific cathedral in its own right, each designed with a distinct purpose and personality. Together, they form the eyes through which humanity watches the birth and death of particles that exist for only the briefest moments. Atlas and CMS are the two giants. Each is the size of a multi-story building and weighs as much as the Eiffel Tower or more. They are general-purpose detectors built to record almost everything that emerges from a collision. Layers of silicon trackers measure the paths of charged particles with microscopic precision. Calorimeters absorb energy and reveal the presence of electrons, photons, and jets of hadrons. Outer chambers catch the elusive muons that can punch through meters of dense material. These two detectors were the instruments that announced the discovery of the Higgs boson in 2012, the particle that completes the Standard Model and explains how other particles acquire mass. Their scale is almost impossible to grasp until you stand beside them. Walking through the cavern that houses Atlas feels like entering the engine room of a starship. Every surface is covered with cables, sensors, and cooling pipes, all arranged with millimeter accuracy so that nothing of importance escapes. Alice is different. It is optimized for the most extreme collisions the machine can produce, those between heavy lead ions rather than ordinary protons. In these impacts, the temperature and density briefly recreate the quark-gluon plasma, the primordial soup that filled the universe microseconds after the Big Bang. Alice's dense tracking systems and specialized particle identification detectors allow physicists to study how this exotic state of matter flows, cools, and eventually freezes into ordinary particles. The data from Alice has shown that the early universe plasma behaves like a nearly perfect liquid, smoother and less viscous than anything we encounter in everyday life. For a few fleeting moments in a cavern under the French-Swiss border, scientists are able to examine a droplet of the universe's original fire. Then there is LHCb, the detector that recorded the quiet anomaly of December 2025. Unlike its larger cousins, LHCb does not surround the collision point completely. It is built as a single-arm spectrometer, stretching forward along the beamline like a giant telescope. This design is deliberate. Particles containing the beauty quark, also called the bottom quark, tend to fly out at small angles, and LHCb is positioned to catch them with maximum efficiency. Its layers of tracking stations, ring-imaging Cherenkov detectors, and muon chambers allow it to reconstruct the decay chains of these heavy particles with extraordinary care. Beauty quarks live only about a trillionth of a second, yet in that brief lifetime, they travel a measurable distance before decaying. HCb's precision vertex detector can resolve that tiny displacement, tagging the beauty hadrons against the background of more common particles. For years, LHCb has been accumulating statistics on rare decays that occur only once in a million or even rarer events. These rare processes act like still ponds. Any unknown influence, any new particle or force too heavy to be produced directly can leave a detectable ripple in the way the decays unfold. The collaboration that runs LHCb includes more than 1,000 scientists from institutions around the world. They check one another's analyses with deliberate adversarial care, searching for every possible source of error before they trust a result. When the December 2025 measurement showed that certain beauty meson decays preferred electrons over muons in a way the Standard Model forbids, the team did not rush to claim discovery. They spent months verifying the finding with independent methods and larger data sets. The discrepancy remained. Standing inside any of these caverns when the detector is closed and the beams are circulating is a strangely quiet experience. The only light comes from the status panels and the occasional glow of diagnostic screens. Overhead, the rock of the Jura Mountains presses down. Outside, ordinary life continues. Inside, the universe is being asked questions at the highest energies humans have ever achieved. The 4 detectors do not simply collect data. They translate the briefest of quantum events into permanent records that can be examined years later by people who were not even present when the collisions occurred. It was LHCb's patient accumulation of rare decays that first revealed the signal that still resists explanation. The other detectors continue their own searches, looking for direct production of new particles or for further clues in the flow of the quark-gluon plasma. Together, they form a single global instrument, distributed across 4 caverns, yet united by a shared purpose: to test the boundaries of the known and to catch the first clear signs that those boundaries are not absolute. The anomaly recorded by LHCb is only one thread. Other experiments, both at CERN and far beyond its borders, have begun to report their own small deviations. When those threads are drawn together, a larger pattern starts to appear. The next part of the story follows that pattern into the heart of the theory the detectors were built to test, the Standard Model itself, and the growing realization that its most successful predictions may no longer be the final word. For nearly 50 years, the Standard Model has stood as the most successful theory in the history of science. It is a compact list of 12 fundamental particles of matter and the forces that govern their interactions, a periodic table of the truly small. With this short catalogue, it explains the structure of atoms, the burning of stars, the behaviour of light, and the radioactive decays that power both nuclear reactors and the Earth's interior heat. Time after time, the model predicted particles that no one had yet seen. Years or even decades later, the machines caught up, and the particles appeared exactly where the equations said they should. The W and Z bosons, the top quark, and finally the Higgs boson in 2012 all arrived on schedule. Each confirmation strengthened the sense that the rulebook was essentially complete. Yet the same physicists who celebrate its successes have always known that pages are missing. Gravity, the force that holds you to the floor and binds galaxies together, has no place in the Standard Model. Dark matter, the invisible substance that appears to make up most of the mass in the universe, is entirely absent. Dark energy, the mysterious pressure that is accelerating the expansion of space, is not mentioned at all. And the model cannot explain why the early universe produced a slight excess of matter over antimatter, the imbalance that allowed anything solid to survive. These are not small omissions. They are fundamental gaps that tell us the current framework, however accurate within its domain, is only an approximation of a deeper reality. The discovery of the Higgs boson felt like the closing of a chapter. Peter Higgs, the theorist who had predicted the particle nearly half a century earlier, sat in the CERN auditorium with tears in his eyes as the announcement was made. Champagne was opened. Speeches were given. For a moment, it seemed that the long search for the final piece of the Standard Model had ended in triumph. In the years that followed, however, the machine continued to run. The detectors continued to collect data, and small discrepancies began to appear in places no one had expected. The rulebook that had never been wrong started to show faint but persistent cracks. One of those cracks is the preference seen in certain rare decays of beauty mesons. According to the Standard Model, electrons and muons should experience the fundamental forces in essentially the same way. Their only important difference is mass. In the delicate processes studied by LHCb, this universality is predicted with high precision. The data, accumulated over years and hundreds of billions of events, shows a small but stubborn deviation. The decays favor one type of lepton over the other more often than the theory allows. The effect is not large enough to claim a discovery under the rigorous 5 sigma standard that particle physics demands. Yet it has refused to fade as more data has been added. Similar tensions have appeared in other measurements, including the magnetic moment of the muon measured at laboratories far from CERN. These anomalies do not yet overturn the standard model. They are more like quiet notes of discord in an otherwise harmonious symphony. But they are consistent enough, and they point in related directions, that many theorists have begun to take them seriously. New particles that couple differently to different generations of leptons, or new forces that distinguish between electrons and muons, could explain the observations. Such additions would not destroy the existing framework. They would extend it, filling in some of the missing pages that have been known for decades. The human side of this story is often overlooked. Teams of young researchers spend years of their careers analyzing a single rare decay channel. Senior scientists who helped build the detectors now find themselves questioning results they once expected to confirm the theory. In seminar rooms and conference halls, the debates are careful, technical, and sometimes intense. No one wants to claim a revolution on the basis of a statistical fluctuation. At the same time, no one wants to miss the first genuine sign that the universe is richer than the current map describes. The standard model remains extraordinarily successful. It continues to describe the vast majority of particle interactions with unmatched accuracy. Yet the small deviations that have accumulated in recent years carry a different kind of weight. They are the first hints that the rulebook, after 50 years of near-perfect performance, may finally be showing the edges of its validity. The next sections of this story follow those hints deeper, into the specific measurements that refuse to settle, and into the larger questions they raise about the origin of matter, the nature of dark components of the cosmos, and the possibility that entirely new layers of reality are waiting just beyond the reach of our present instruments. The machine keeps running, the data keeps arriving, and the quiet tension between prediction and observation continues to grow. In the winter of 2025, a specialized detector at CERN recorded a result that still refuses to settle. The instrument is called LLHCb, and its entire purpose is to study the behavior of particles that contain the beauty quark, one of the heavier and more elusive building blocks of matter. These beauty particles live for only about a trillionth of a second before they decay into lighter pieces. Most of the time, the decays follow patterns that the standard model predicts with high precision. Once in a great while, however, a particularly rare type of decay occurs, a process so delicate that any unknown influence can leave a visible mark. Physicists call this rare process a penguin decay, a name that began as a joke decades ago when a young theorist lost a bet and had to insert the word into a scientific paper. The diagram that describes the decay looked a little like a penguin standing upright, and the nickname stuck. Behind the playful label sits a serious experimental strategy. Because the process is so rare and so carefully predicted, it acts like a still pond. Drop a pebble and every ripple is easy to see. If a new particle or force is operating just beyond the reach of direct detection, it can disturb the angles and rates of these decays in ways the standard model cannot explain. LHCb was built to watch that pond with extraordinary patience. Over several years of collisions, the collaboration recorded hundreds of billions of beauty particles. From that mountain of data, they extracted the tiny fraction that followed the rare penguin pathway. Then, they measured not only how often the decays happened, but the precise angles at which the resulting particles flew outward. The standard model makes a clear prediction for those angles. Nature, according to the 2025 analysis, did not obey. The measured distribution sat consistently to one side of the expected value. The discrepancy was not dramatic, yet it had grown stronger as more data was added, reaching a level that physicists describe as 4 sigma, strong enough to demand attention, but not yet decisive. The reaction inside the collaboration was cautious. Analysis teams re-examined every possible source of experimental bias. Independent groups repeated the measurement with different techniques. Theoretical calculations were scrutinized for missing higher-order effects. Months of work followed. The deviation remained. In seminar rooms, the discussions were quiet but intense. Young researchers who had spent years on the analysis felt both excitement and the weight of responsibility. Senior physicists who had helped design the detector found themselves confronting the possibility that the result might be the first clear sign of physics beyond the standard model. What makes the finding especially intriguing is that it does not stand alone. Similar tensions have appeared in related measurements of beauty decays and in the magnetic properties of the muon studied at laboratories across the Atlantic. All of them hint at the same underlying idea. Something is distinguishing between different types of leptons in ways the current theory forbids. One popular class of explanations involves new particles called leptoquarks, hypothetical objects that could link quarks and leptons directly. Another involves a heavier cousin of the known Z boson that couples more strongly to one generation of particles than another. Neither has been observed directly, yet both could produce the subtle effects now appearing in the data. The people who work on these analyses understand that a 4 sigma result is still only a strong hint. History is filled with anomalies that grew and then faded as more data arrived or as theoretical calculations improved. At the same time, they know that some of the most important discoveries in physics began as small, persistent discrepancies that refused to go away. The 2025 penguin measurement has joined that short list of results that keep the field awake at night. Outside the analysis rooms, the collider continues its work. New data is being collected at higher intensity than ever before. The same rare decays are being recorded again and again. In the coming years, the statistical power will increase, and the question will become sharper. Either the deviation will settle back into agreement with the standard model, or it will grow until it can no longer be denied. Either outcome will matter. Confirmation would open a new chapter in particle physics. Disappearance would reaffirm the extraordinary accuracy of the existing theory. For the moment, the signal sits in the middle ground, quiet, stubborn, and unexplained. The deeper significance of the anomaly becomes clearer when it is placed beside the larger mysteries the standard model has never been able to solve. The most personal of those mysteries is the simple fact that matter exists at all. In the first moments after the Big Bang, matter and antimatter should have been created in equal amounts and then annihilated each other completely. The universe should contain nothing but light. Instead, a tiny excess of matter survived, and from that excess came every star, every planet, and every living thing. The penguin decays and the related lepton anomalies may be faint echoes of the same new physics that produced that crucial imbalance. The next part of the story follows that connection into the question of why anything exists. The most personal mystery in all of physics is the simple fact that you exist. In the first moments after the Big Bang, the universe should have contained equal amounts of matter and antimatter. Every particle should have met its opposite and annihilated in a flash of pure energy, leaving behind nothing but radiation. The cosmos should be empty. Instead, a tiny imbalance appeared. For every billion particles of antimatter, there was roughly 1,000,000,001 particles of ordinary matter. That 1 in a billion surplus survived the Great Annihilation and became everything we see: stars, planets, oceans, and living beings. The Standard Model can generate a small preference for matter through a process called charge parity violation, yet the amount it produces is far too weak to explain the universe we actually inhabit. Something else must have tipped the scales. The rare decays studied by LHCb were designed in part to search for stronger sources of that preference. Beauty particles are expected to show larger differences in the way they treat matter and antimatter than lighter particles do. For years, the experiment has measured these differences with increasing precision. The results confirm that charge parity violation exists in the beauty sector, yet the observed effect is still nowhere near large enough to account for the cosmic imbalance. The same data set that revealed the lepton anomaly also deepened the puzzle of why matter won. If new particles or forces are influencing the way beauty mesons decay into electrons and muons, those same influences could have operated in the extreme heat of the early universe and produced the crucial excess of matter. Imagine the first fraction of a second after the Big Bang as a seething fireball in which particles and antiparticles flashed in and out of existence at unimaginable rates. Any slight difference in the way new physics treated the two sides of the ledger would have been magnified by the enormous numbers involved. A process that looks like a small statistical tilt in a modern detector could have been decisive when the entire observable universe was still smaller than a city. The anomalies recorded today may therefore be faint fossils of the mechanism that allowed anything solid to survive. Scientists at CERN have also built dedicated experiments to study antimatter directly. They trap antihydrogen atoms, the antimatter version of the simplest element, and compare their properties with ordinary hydrogen to extraordinary precision. So far, the two appear almost identical. Almost. Small statistical differences continue to appear at the edge of measurement sensitivity, never quite strong enough to claim a discovery, yet never quite disappearing. These hints, together with the lepton anomalies and the shortfall in known charge parity violation, form a single growing question. What hidden physics produced the matter-dominated universe we inhabit? The people who work on these measurements feel the weight of the question in a personal way. Many of them entered the field hoping to understand the origin of mass or the nature of the forces. They find themselves instead confronting the origin of existence itself. In quiet conversations after seminars, the same thought surfaces again and again. If the Standard Model cannot explain why there is something rather than nothing, then the anomalies we are seeing may be the first cracks through which a deeper explanation will eventually appear. The connection is still only a possibility. No one has yet demonstrated that the same new physics responsible for the penguin deviation is also responsible for the cosmic matter excess. Yet the logic is compelling enough that theorists have begun to construct models in which both puzzles are solved by the same extension of the Standard Model. Leptoquarks, or new force carriers that distinguish between particle generations could, under the right conditions, generate the required asymmetry in the early universe while leaving the subtle fingerprints now appearing in the data. As more collisions are recorded and the statistical power of the measurements increases, the question will become sharper. Either the anomalies will fade and the origin of matter will remain one of the great unsolved problems, or they will strengthen and point toward a common solution. For the moment, they sit together as two sides of the same unfinished story. The universe contains matter. The detectors record small preferences that should not exist. And somewhere between those two facts may lie the reason that anything exists at all. The next thread in the story takes us to an even earlier moment, when the universe was still a hot soup of free quarks and gluons, and to the machine that can recreate that primordial state for a fleeting instant under the French-Swiss border. Creating and studying this state is an extraordinary technical achievement. The ions must be accelerated to nearly the speed of light and brought into collision with micrometer precision. The detector must record the resulting spray of particles before the plasma cools and freezes back into ordinary matter, a process that lasts only a few trillionths of a second. Yet the measurements are precise enough to map how the plasma expands, how it cools, and how the free quarks and gluons eventually recombine into the protons, neutrons, and other particles that make up the world we inhabit. These experiments do more than recreate a lost chapter of cosmic history. They test our understanding of the strong nuclear force, the interaction that binds quarks together under normal conditions. The theory that describes this force is called quantum chromodynamics, and it is notoriously difficult to calculate when the energy is low and the quarks are tightly bound. By studying the plasma at the opposite extreme, when the quarks are free, physicists gain new insight into the force that holds ordinary matter together. The results feed back into theoretical models and improve our ability to predict how matter behaves under the most extreme conditions, including those found in the cores of neutron stars. There is also a quiet connection to the larger mysteries. The same early universe conditions that produced the quark-gluon plasma were the setting in which the slight excess of matter over antimatter must have arisen. Any new physics that influenced particle behavior in those first moments could have left traces both in the cosmic matter imbalance and in the subtle anomalies now appearing in modern detectors. The plasma experiments do not yet show direct evidence of that new physics, but they provide an independent window onto the same epoch of cosmic history. The scientists who work on ALICE speak of the plasma with a mixture of technical precision and genuine wonder. They are, in a real sense, the first people to examine a state of matter that last existed when the universe was less than a second old. In the control rooms and analysis centers, the data arrive as streams of numbers, yet everyone understands that those numbers describe a droplet of the original fire. The measurements continue to improve as the collider delivers more heavy ion collisions at higher energies. Each new data set refines the picture of how the plasma flows and freezes, adding another page to the lost first chapter of the cosmos. The story of the primordial soup is only one thread. While Alice examines the earliest moments of the universe, other experiments continue to probe the structure of matter itself at the smallest scales. One of the most surprising recent findings involves particles that should not exist according to the simplest version of the quark model. Exotic combinations of 5 quarks bound together in ways that challenge long-held assumptions. The next part of the story follows those unexpected structures and the questions they raise about how deeply we understand the strong force that holds the visible universe together. For more than 50 years, the simple picture of hadrons seemed complete. Protons and neutrons were three-quark states. Mesons were quark-antiquark pairs. That tidy classification explained the entire zoo of particles produced in earlier accelerators. Then, the data began to show something that did not fit. In the decay products of beauty mesons, LHCb recorded clear signals of particles containing 5 quarks. These pentaquarks are not predicted by the basic quark model. Their existence forces a deeper question. How many ways can the strong force bind quarks together, and what other hidden structures might still be waiting to be found? The first candidates appeared in 2015. Further measurements with larger datasets confirmed them and revealed additional states. By late 2025, the evidence had grown strong enough that the collaboration could speak of a family of 5 quark particles rather than isolated curiosities. One of the newest states, provisionally labeled P C4312, showed a decay pattern that suggested a more intricate internal arrangement than earlier examples. The experimental challenge was enormous. Trillions of collisions had to be sifted. Rare decay chains had to be reconstructed with extreme care. Background processes that could mimic the signal had to be understood and subtracted. Only after years of cross-checks did the results stand. Theorists are still debating what these objects really are. One possibility is that they are tightly bound packages of 5 quarks, genuine new citizens of the particle zoo. Another is that they are loosely bound molecules in which a conventional 3-quark baryon and a meson orbit each other for a brief time before falling apart. Both interpretations challenge the older, simpler view of the strong force. Quantum chromodynamics, the theory that describes quark interactions, is extremely successful at high energies, yet becomes almost impossible to calculate exactly when quarks move slowly and bind into complex states. The pentaquarks supply new data points that any complete theory must eventually explain. Inside the collaboration, the discovery produced a mixture of satisfaction and caution. Satisfaction because the signal was clean and the statistical significance high. Caution because exotic hadrons have a history of appearing and then dissolving under closer scrutiny. The team therefore published the result with careful language, inviting the rest of the field to examine the data and attempt independent confirmation. Other experiments are now searching for similar states, and lattice calculations are being refined to predict the masses and decay modes more accurately. These 5-quark structures matter for reasons that go beyond particle catalogues. They reveal that the strong force is richer and more versatile than the textbook diagrams suggest. The same force that holds ordinary protons together can also assemble temporary, more elaborate configurations. Understanding those configurations improves our models of nuclear matter under extreme conditions, including the interiors of neutron stars, where densities reach values that may favor multi-quark states. In that sense, the pentaquarks are not merely laboratory curiosities. They are windows onto the behavior of matter in environments we can never visit directly. The appearance of these unexpected particles also reinforces a larger theme running through the recent data. Again and again, the standard model and its simplest extensions describe most observations with impressive accuracy, yet small corners of the data refuse to fit. Rare decays tilt the wrong way. Magnetic moments disagree by tiny amounts. Exotic hadrons appear where the basic counting rules said they should not. Each anomaly by itself can be debated. Taken together, they create a quiet but persistent impression that the map of the subatomic world is still incomplete. As the collider continues to deliver higher luminosity, the sample of beauty mesons will grow, and the properties of the pentaquarks will be measured with greater precision. Masses, widths, and quantum numbers will become sharper. The molecular versus compact debate may be settled. New states may appear. Whatever the final picture, the discovery has already expanded the known landscape of matter. The strong force, once thought to produce only a limited set of combinations, has shown that it can build more elaborate structures than anyone expected. The next thread in the story moves from these unexpected bound states to a different kind of anomaly, one measured not at CERN but at a laboratory across the Atlantic, yet connected by the same underlying suspicion that new physics is at work. Across the Atlantic, in the flat fields of Illinois, another experiment has been quietly challenging the same rulebook. The particle at the center of this story is the muon, a heavier cousin of the electron that is created in the upper atmosphere every time cosmic rays strike air molecules. Muons rain down through the atmosphere, through buildings, and through our bodies at a rate of thousands per minute. They are ordinary enough to be almost invisible in daily life, yet their magnetic properties have become one of the most precise and puzzling measurements in all of physics. A muon behaves like a tiny spinning magnet. When it is placed in a magnetic field, its spin axis wobbles at a rate determined by a quantity called the magnetic moment. The standard model predicts this rate with extraordinary accuracy after decades of theoretical work that accounts for the influence of every known particle and force. The calculation is one of the great achievements of quantum field theory. When experimenters set out to measure the same quantity, they expected confirmation. What they found instead was a small but persistent disagreement. The first clear sign appeared at Brookhaven National Laboratory. Later, the entire apparatus, a 50-foot wide superconducting magnet weighing 17 tons, was transported with extreme care to Fermilab so that the measurement could be repeated with higher precision and better control of systematic errors. The journey itself became a minor legend. The magnet could not be tilted more than a fraction of a degree, so it traveled slowly across the country on a custom vehicle while crowds gathered to watch. Once installed and calibrated, the new experiment confirmed the earlier discrepancy and strengthened it. The muon was wobbling slightly faster than the standard model allowed. The difference is tiny in everyday terms, yet in the world of high-precision physics, it is large enough to demand an explanation. One possibility is that the theoretical calculation still lacks some subtle contribution from known physics. Another is that new particles, too heavy or too weakly interacting to have been seen directly, are influencing the muon through the quantum loops. These virtual particles would appear only as a small extra contribution to the magnetic moment, exactly the kind of effect now observed. The same class of new particles that might explain the lepton anomalies at LHCb could also account for the muon's behavior. The scientific community has treated the result with characteristic caution. Independent groups have re-examined both the experimental analysis and the theoretical prediction. Some adjustments to the theory have reduced the tension, others have left it largely intact. As of the most recent updates, the discrepancy remains significant enough that many physicists regard it as one of the strongest existing hints of physics beyond the standard model. In 2026, the work was recognized with a major international prize, a formal acknowledgement that the anomaly can no longer be dismissed as a temporary curiosity. What makes the muon result especially powerful is its connection to the measurements at CERN. Both point toward new interactions that treat different generations of leptons unequally. Both suggest that the neat separation of particle families assumed by the standard model may be incomplete. If a common explanation exists, it would link experiments separated by an ocean and by very different techniques into a single emerging picture. Theorists are already exploring models in which leptoquarks or new force carriers simultaneously shift the muon magnetic moment and alter the rare beauty decays. None of these models is yet confirmed, yet the fact that the same ideas can address multiple anomalies gives them added weight. Inside the laboratories, the mood is one of disciplined excitement. The teams that spent years refining the muon measurement understand that a genuine discovery of new physics would be historic. They also understand that extraordinary claims require extraordinary evidence, and they continue to search for every possible source of error. At the same time, the result has already changed the conversation. What was once a single isolated tension has become part of a broader pattern that includes the penguin decays, the shortfall in matter, antimatter asymmetry, and the appearance of unexpected multi-quark states. The rulebook is still extraordinarily successful, yet the number of places where it is being gently tested continues to grow. The muon keeps arriving from the sky, keeps passing through the Earth, and keeps carrying a small, unexplained excess in its magnetic moment. That excess is a quiet invitation. It asks whether the particles and forces we have catalogued are truly all there is, or whether a deeper layer of reality is beginning to show itself through the most precise measurements ever made. The next part of the story turns to the largest and most persistent of all the missing pieces, the invisible components that appear to make up most of the universe. Most of the universe is missing. Everything we can see and touch, every star, planet, gas cloud, and living organism accounts for only about 5% of the total mass energy content of the cosmos. The remaining 95% is invisible. Roughly 27% appears to be dark matter, a substance that exerts gravity yet does not emit, absorb, or reflect light. The other 68% is dark energy, a mysterious pressure that is causing the expansion of space itself to accelerate. These two components dominate the universe, yet the standard model contains no particle or force that can explain either of them. Dark matter first revealed itself through the motion of galaxies. Stars at the outer edges of spiral galaxies orbit far faster than the visible mass can explain. The only way to keep those stars from flying outward is to assume a large amount of unseen mass distributed in a halo around each galaxy. The same invisible mass bends the light of distant objects through gravitational lensing and shapes the large-scale structure of the cosmic web. Without dark matter, the universe would look entirely different. Galaxies would be smaller, fewer, and unable to hold themselves together. Decades of searching have failed to identify the particle responsible. Detectors buried deep underground watch for the rare occasions when a dark matter particle might collide with ordinary matter. The Large Hadron Collider looks for events in which energy and momentum go missing, the signature of a particle that escapes the detectors without interacting. So far, both approaches have returned only upper limits. Whatever dark matter is, it interacts even more weakly than neutrinos, or it is heavier or lighter than the ranges currently being probed. Dark energy is stranger still. In the late 1990s, observations of distant supernovae showed that the expansion of the universe is not slowing down under the pull of gravity, as everyone expected. it is speeding up. Something is pushing space apart with ever-increasing strength. The simplest explanation is a constant energy density inherent to the vacuum itself, the cosmological constant first considered by Einstein. Yet the value required by observation is astonishingly small compared with the vacuum energy suggested by quantum field theory, a discrepancy of many orders of magnitude that remains one of the deepest fine-tuning problems in physics. Alternative ideas treat dark energy as a dynamic field that changes with time, but no experiment has yet distinguished between these possibilities. The anomalies recorded at CERN and Fermilab do not yet provide a direct solution to either mystery. They do, however, keep open the possibility that the same new physics responsible for the lepton preferences and the muon magnetic moment might also generate candidates for dark matter. Some theoretical models that introduce leptoquarks or additional force carriers automatically contain stable, weakly interacting particles that could fill the dark matter role. Other models link the vacuum energy problem to the same extensions that address the hierarchy of particle masses. None of these connections is proven, yet they illustrate how a single crack in the standard model might eventually illuminate several of the largest unanswered questions at once. The human response to these invisible components mixes frustration with awe. Astronomers map their gravitational effects across billions of light years. Particle physicists design ever more sensitive detectors in the hope of catching a single interaction. Cosmologists incorporate both dark matter and dark energy into precision models of the universe's evolution and fate. The accelerating expansion driven by dark energy suggests that the universe will continue to grow colder and emptier, galaxies drifting beyond each other's horizons until each is alone in a vast darkness. That long-term forecast is based on the assumption that dark energy remains constant. If it evolves, the future could be different. The data cannot yet decide. In the meantime, the visible 5% continues to be studied with increasing precision. The same machines that search for dark matter particles also refine our understanding of ordinary matter, producing the rare decays and exotic hadrons that have already challenged the rulebook. The invisible majority of the cosmos remains silent, detectable only through the gravity it exerts and the acceleration it causes. Yet the quiet anomalies appearing in the visible sector keep alive the hope that the two realms are not entirely separate. A deeper theory might one day explain both the behavior of beauty mesons and the dominance of dark components with the same set of principles. Until that theory arrives, the universe remains mostly hidden, its greatest constituents still unnamed and its ultimate fate still uncertain. The next part of the story turns from these cosmic scale mysteries to the more intimate philosophical questions they raise about the nature of reality and the limits of human understanding. The anomalies and missing pieces we have followed do not remain confined to laboratory notebooks and theoretical papers. They reach into questions that have occupied human thought for centuries. What is the ultimate nature of reality? How stable is the world we inhabit? And what does it mean that conscious beings can ask these questions at all? Particle physics, at its deepest level, is not only a technical discipline. It is an empirical way of confronting the foundations of existence. One of the more unsettling ideas that emerges from current theory is the possibility that our universe occupies a false vacuum. The Higgs field, whose discovery completed the standard model, may not sit at the absolute lowest energy state available to it. Calculations suggest that the present vacuum could be metastable, stable enough to last for times far longer than the current age of the cosmos, yet not guaranteed against an eventual quantum transition. If such a transition occurred, a bubble of true vacuum would form and expand at the speed of light, rewriting the masses of particles and the strengths of forces inside it. Everything we know would be replaced by a different set of physical laws. Most estimates place the expected lifetime of the present vacuum at an enormous value, far beyond any practical concern. Still, the mere possibility forces a confrontation with fragility. The same field that gives particles their mass, and therefore allows atoms and chemistry and life, might not be the final configuration of reality. The recent anomalies add a further layer of reflection. If new physics exists at higher energy scales, it could influence the shape of the effective potential that determines vacuum stability. Some extensions of the standard model improve the apparent stability. Others can make the metastability more pronounced. No one can yet say which possibility is correct. The question remains open, hanging over the more concrete experimental results like a distant horizon. These considerations do not produce panic in the scientific community. They produce a particular kind of humility. The instruments at CERN and elsewhere are the most powerful ever built for probing the smallest scales. Yet they still leave the largest questions only partially answered. Gravity remains outside the quantum framework. The majority of the universe's content remains unidentified. The origin of the matter excess remains incomplete. Each successful measurement sharpens the remaining mysteries rather than eliminating them. In the control rooms and seminar halls, the daily work continues with technical focus. Data are calibrated, backgrounds subtracted, systematic uncertainties quantified. Yet, in quieter moments, many of the same researchers acknowledge the larger context. They are participants in a centuries-long effort to understand the rules that make a habitable universe possible. The fact that the rules appear fine-tuned enough to permit complexity, and that we are here to notice the fine-tuning, remains one of the deepest puzzles. Some see it as evidence of deeper principles yet to be discovered. Others simply accept it as the boundary condition of the reality we find ourselves inside. The philosophical edge of the subject is not a distraction from the science. It is the reason the science matters to people beyond the professional community. When a rare decay tilts the wrong way, or a magnetic moment disagrees by a few parts in a billion, the discrepancy is technical. When that discrepancy is placed beside the existence of matter, the invisibility of most of the cosmos, and the possible metastability of the vacuum, it becomes part of a larger conversation about the kind of universe we inhabit and the limits of what we can know. The experiments do not answer the oldest questions. They refine the terms in which those questions can be asked. As the machines prepare for higher intensities and the theorists explore new frameworks, the conversation continues. The next generation of colliders may close some of the present gaps or open deeper ones. Either outcome will reshape the boundary between the known and the unknown. For now, the boundary remains where the current data leave it, a set of precise successes surrounded by a set of equally precise absences and a handful of small, stubborn signals that refuse to fit the existing map. The final part of this story looks toward the instruments and ideas that will carry the search forward, and toward the enduring human impulse that makes the search worthwhile. The machines now running at CERN will not be the final word. Even as the Large Hadron Collider continues to deliver higher luminosity and more precise data, plans are already taking shape for the instruments that will follow it. The most ambitious proposal is a future circular collider. a ring nearly 100 kilometres in circumference that would dwarf the present tunnel. In its first stage, it would operate as an electron-positron collider, a precision factory for studying the Higgs boson and other known particles with unprecedented accuracy. Later, it could be converted into a proton-proton collider, reaching energies up to 100 tera-electron volts, nearly 8 times higher than the present machine. At those energies, the production of heavy new particles that are currently out of reach would become possible, and the subtle anomalies that now appear only as statistical tensions could be confronted with decisive clarity. Other concepts are also under study. A compact linear collider would accelerate electrons and positrons in a straight line, avoiding the energy losses that limit circular machines at very high energies. Muon colliders, still at an earlier stage of development, offer the prospect of combining high energy with a relatively compact footprint. Each design carries its own technical challenges and scientific strengths. The choice among them will depend on the results still to come from the present generation of experiments, on advances in superconducting magnet technology, and on the willingness of the international community to commit resources on a scale that exceeds even the original investment in the Large Hadron Collider. Whatever form the next machine takes, its purpose will remain the same: to test the boundaries of the known and to search for the physics that lies beyond. The anomalies recorded in recent years have already begun to sketch the outline of that larger territory. Rare beauty decays that prefer one type of lepton over another, a muon magnetic moment that refuses to match the most precise calculations, unexpected multi-quark states, and the persistent silence of dark matter and dark energy all point toward a reality richer than the standard model alone can describe. The next generation of colliders will be built to decide whether those pointers are genuine or whether they will ultimately dissolve under closer scrutiny. Either outcome will advance understanding. Confirmation would open an entirely new chapter. Disappearance would reaffirm the extraordinary power of the existing framework and force theorists to look elsewhere for solutions to the remaining cosmic puzzles. The human dimension of this long effort is easy to overlook amid the technical details. Thousands of scientists, engineers, and students from more than 100 countries continue to work at CERN and at laboratories around the world. Many will spend entire careers on a single measurement or a single theoretical calculation. Some will see their results strengthen into discoveries. Others will watch promising signals fade. The collective enterprise continues regardless, driven by the same curiosity that first led people to ask what the world is made of and why it exists at all. In an age often marked by division, the laboratories remain places where national borders recede in the face of shared questions that belong to everyone. The technologies developed for these experiments have already spread far beyond particle physics. The World Wide Web began at CERN as a tool for sharing information among collaborating scientists. Advances in superconducting, magnets, cryogenics, vacuum technology, and high-speed computing have found applications in medicine, materials, science, and industry. The pursuit of fundamental knowledge continues to yield practical benefits that no one fully anticipates at the outset. Yet the deepest value of the work is not utilitarian. It lies in the enlargement of the human perspective. Each new measurement, whether it confirms or challenges existing theory, adds to the accumulating record of how the universe behaves at its most basic level. That record becomes part of the common inheritance of the species. As the present run of the Large Hadron Collider proceeds and the planning for its successors advances, the central questions remain open. Will the lepton anomalies grow into clear evidence of new forces or particles? Will the muon discrepancy be resolved by improved theory or by the discovery of physics beyond the standard model? Will dark matter finally appear in a detector, or will its nature require an entirely different approach? Will the vacuum we inhabit prove stable on cosmic timescales, or will future calculations and measurements alter that assessment? No one can yet say. The data will decide, as they always have. For those who follow these developments from outside the laboratories, the story offers something rarer than definitive answers. It offers contact with the frontier itself. The same species that once watched the stars with unaided eyes now builds machines that recreate the first moments of the cosmos and measure effects at the level of parts in a billion. The distance between those two activities is the measure of what systematic curiosity can achieve. The remaining distance, the question still unanswered, is the measure of how much further there is to go. The universe continues to present itself as both intelligible and inexhaustible. The rulebook that has guided physics for half a century remains extraordinarily successful, yet the small, stubborn deviations that have appeared in recent years keep open the possibility that the book is still incomplete. In the caverns beneath the Franco-Swiss border, in the analysis rooms where data are examined, and in the theoretical institutes where new ideas are tested against those data, the work of reading the next pages continues. The outcome is not predetermined. It will be written by the collisions still to come, by the detectors still to be built, and by the people who devote their working lives to the task. Until those results arrive, the invitation remains the same. Look closely, question carefully, allow the evidence to lead where it will. The cosmos is under no obligation to match our expectations, yet it has so far proven willing to answer the questions we are patient and precise enough to ask. The next answers may confirm the map we already possess, or they may force us to redraw its boundaries. Either possibility enlarges the domain of what is known. That enlargement is the enduring purpose of the entire enterprise, and the reason the machines keep running through the nights and years beneath the quiet fields of the border. The story that began with a quiet discrepancy in a rare particle decay has now travelled across the full landscape of modern fundamental physics. From the engineering marvel of the Large Hadron Collider itself, through the specialised detectors that watch every collision, to the standard model's extraordinary successes and its equally striking absences, the same underlying tension has appeared again and again. Small, carefully measured effects refuse to settle into the expected patterns. Beauty mesons decay with a slight preference that should not exist. The muon carries a magnetic moment that disagrees with the most precise calculations. Unexpected 5-quark states challenge the simplest picture of the strong force. The cosmic excess of matter over antimatter remains quantitatively unexplained. Dark matter and dark energy continue to dominate the universe while remaining invisible to every direct probe so far devised. Even the stability of the vacuum we inhabit carries a theoretical question mark. None of these issues has yet produced a definitive discovery of physics beyond the standard model. Each remains at the level of tension or strong hint, rather than confirmed new phenomenon. That status is important to keep in view. Particle physics advances by the slow accumulation of evidence, by the gradual elimination of experimental and theoretical uncertainties, and by the eventual appearance of results that can no longer be reconciled with existing frameworks. The present collection of anomalies may ultimately dissolve under the weight of more data and improved calculations. It may instead coalesce into the first clear outline of a larger theory. The experiments now running and the machines still on the drawing board exist to decide between those possibilities. What remains constant is the human activity that makes the decision possible. In control rooms, analysis centers, and theory institutes, people continue the patient work of measurement and interpretation. They calibrate detectors, refine simulations, debate systematic uncertainties, and test new theoretical constructions against the latest results. The work is technical, often slow, and frequently inconclusive in the short term. Over longer spans, it has produced the most accurate description of the physical world ever achieved, and it continues to press against the edges of that description. The same curiosity that once led observers to track the planets and weigh the Earth now drives the construction of instruments that recreate the first moments of the universe and measure effects at the level of parts in a billion. The practical consequences of this effort have already reached far beyond the laboratories. Tools and techniques developed for particle physics have found uses in medicine, computing, materials, science, and many other fields. The deeper consequence is cultural. A species capable of asking what the universe is made of, and of building the means to answer, has enlarged the scope of shared knowledge. Each confirmed result, and each unresolved tension, becomes part of the common record. Future generations will inherit both the map and the open questions, and will continue the work with instruments and ideas that cannot yet be imagined. For the present, the Large Hadron Collider keeps circulating its beams. The detectors keep recording. The data keep arriving. The small discrepancies that first drew attention remain under active study, neither confirmed as new physics nor dismissed as artifacts. In that suspended state, the central invitation of the subject is clearest. Look at the evidence without preconception. Allow the measurements to constrain the imagination rather than the reverse. Accept that the universe is under no obligation to be simple, yet has so far proven responsive to careful and sustained inquiry. The questions that first surfaced in a specialized detector at CERN now sit within a wider conversation that includes the origin of matter, the composition of the cosmos, and the long-term fate of the vacuum itself. No final answers are yet in hand. The tools required to seek them are either operating or in active preparation. The people who will use those tools are already at work. The rest of us can follow the results as they appear, recognizing that each new measurement, whether it resolves a tension or deepens it, adds to the accumulating understanding of the reality we inhabit. That understanding is incomplete, as it has always been. The effort to extend it continues, underground and across the world, one collision, one analysis, and one careful question at a time.